recording. Okay, so now we are going to work with complex eigenvectors. You've had experience with complex eigenvectors and complex eigenvalues from section 5.5. All right, let me give you a moment to copy down this example. Okay, so here we're going to suppose that we have a complex valued solution to this linear system of differential equations. And you notice I'm suppressing the t, but we know x is a function of t. Okay, so you can have complex valued solutions. Well, you can have complex valued solutions to linear systems of differential equations. And that's fine. That's fine. if that's the case, there are two components to the complex eigenvector. So like, a complex eigenvector, let me just see here, one moment. Hold on. Let me just see here, one moment, class. Yeah, so, I mean, if you had something like, say you had 3 plus I and -1 minus 4I. Okay, well, you can write that as 3, -1, hold on, 3, -1, plus I times 1, 4. Now this is 1, -4, right? This is just an imaginary thing, right? But the point is that you can dissect a complex vector. You can rewrite a complex vector as a vector with real numbers in it, plus I times another vector with real numbers in it. So this vector x called xret and this vector x sub imt have real numbers in it. So in this case, x sub real t would be, well, I got to be careful. I don't have t's there, but you get the general idea. You get the general idea. You can take a complex eigenvector and re-express it this way. And the nice thing about that is it generates two more solutions to the system of differential equations called x real and x imaginary of t. Now this is not hard to prove. This is not hard to prove. Okay, so what I'm doing here is I'm saying, okay, let's go ahead and differentiate this. Actually, what I'm going to do, I think, class, I really do need to get to the next example. So I'm going to sort of go through this rather quickly. You probably, you're welcome to copy it down later. This is, I'm just trying to just sort of relax and look at what's being shown here. So then we can get to the example. This is, so, okay, x of t is equal to x real of t plus the imaginary plus I times x sub im of t. And incidentally, we're told that d dt of this vector is equal to a times the vector. We're told that because in the problem we're told that this is a complex valued solution. We're given that. So that means when you take the derivative of that vector, it's going to equal a times that vector. Now, what I can do is, again, here now, we have the derivative of a sum. The derivative of a sum of two vectors is the sum of the derivatives. Okay. And then what I can do is on the second part where I take the derivative here, I can pull out the constant I. Yes, I is an imaginary number, but it's also a constant. It's not a function of t, right? So I can rewrite the derivative of x of t as the derivative of my x real part plus I times the derivative of my x imaginary part. Okay? But I can set that then, well, first, are there any questions up to here? Are there any questions up to there? Okay, Kevin's good. All right, Christy's good. All right, very good. Well, now, remember, so now going from this step to this step, I say all of a sudden, hey, this here, the sum of these vectors is equal to a times x real plus I times a times xi. Where do I get that from? Well, I get that from up here. I get that from up here. Okay, this here, a times x real plus I times x imaginary, can be written as a times, if I distribute the matrix A, I'll get a times x real plus I times x imaginary. Okay, so this is true. This is not a problem. Not a problem at all. Now, what's really cool is this. Okay, I have here a complex eigenvector equaling another complex eigenvector. This means that a times x real is going to have to equal the derivative of x real, and a times x prime is going to have to equal the derivative of x prime. It has to. There's no other choice, right? Because the two vectors are equal. Well, this shows then that x real and x prime are solutions to our system, our linear system of differential equations. Okay, are there any questions on that? Okay. Want to make sure we're comfortable. All right. So you see, what we're going to be doing is we're going to be looking at a particle moving, another particle moving in the x1, x2 plane. Okay, another particle moving in the x1, x2 plane. And it's going to have the matrix A is going to have complex eigenvalues and complex eigenvectors, and we want to study the trajectory of the particle. So if there are no questions on this, let me upload the next example. One moment. Be just a moment. Okay, now let me upload it. One moment. Should upload well. Good. Okay, uploading now. Now we're going to look at an example. So I'm sorry we probably won't have any time for classwork tonight. We do need to finish this section, and we're still a little behind on the syllabus. So we do have to finish section 5.7, and but it's okay. You're having fun, right? You're having fun. Okay, good, good. All right, I love it. Thank you, Solomon. Thank you, Samuel. All right, take a moment to copy this example down. Well, Matthew, we're going to be okay. We're going to be okay. I mean, we don't want to fall behind. We can fall a little bit behind because we can catch up if we're a little bit behind. But if we get too far behind, then But it's sort of a balance because I don't want to just cover stuff and not be able to answer questions and help people feel comfortable. It's kind of a balance. A planar force field is basically, I mean, a planar force field is a force field located in the x1, x2 plane. And what we're studying here are particles moving in these planar force fields. So, you have two differential equations. You have a dx1 of t and a dx2 of t. x1 of t, okay, describes the motion, horizontal motion of the particle. x2 of t is the vertical motion. So together, when you have horizontal and vertical motion acting on a particle, you're moving in a plane, in an x1, x2 plane. There's a force field acting that's causing these particles to move the way they're moving. A force field, yeah, like an electromagnetic field. That's right, Matthew. Or a velocity field, like if you have some kind of velocity field, like wind, for instance, wind or a river. And actually, in Calculus 3, you're going to be seeing some different force fields. And that's Math 280. You will, and incidentally, Dr. Duty's teaching that in the spring. I'm teaching that. Well, the textbook we use here, Matthew, does deal with force fields, and of course, instructors ideally are supposed to talk about that. But it comes up later in chapter 13. It comes up later in Math 280. All right, so let me give you a moment to copy that. Very good questions tonight. Very good questions. I think this is some of the most beautiful math, around. And I love it that we're tying. I mean, if you take differential equations, and then you'll learn about, solving linear systems of differential equations. They'll give you the techniques with eigenvectors, eigenvalues. Being that you've had linear algebra, you will understand why those techniques why they work. Yeah, vector fields, force fields, sure. Same, that's right, Matthew. Okay, are we ready to move to look at start with the solution, or do you need a little more time to copy? Are we good? All right. So you notice what I did here is the two differential equations. I didn't write them out, but the fact that you know the matrix A means you know what the two differential equations are: dx1 dt, dx2 dt. Initially, our particle is going to start at 3,3. Okay, and now what's the first thing that we need to do here for this problem? What's the first thing that we need to find? What's the first thing we need to find? Let's say you're working this out in homework. Eigenvalues, right? And eigenvectors. Good. Because we learned that if we can find those, we can get the solution. Okay, well, so it may be shown, and you can, using MATLAB. Okay. Having a little, hold on. Using MATLAB. Okay, that the matrix A will have these eigenvalues and eigenvectors. And maybe what I'll do is just go into MATLAB here. Open it up. And I'm actually going to do this right in MATLAB as well. It's worth doing. So you'd also go into MATLAB, type the matrix A in, and get out your eigenvalues and eigenvectors. Okay, I'll come back to the solution, but let me just show you in MATLAB. Okay, so I typed in the matrix A, and I use that eigsimA command, and the EVR gives me my eigenvectors, and the EVL, the diagonal of EVL, gives me the eigenvalues. Now, the eigenvectors, the MATLAB gives it as negative I over 2. And by the way, I had, let me just see one thing here. Let me just see one thing. Done. All right. I used format. I have to do CLC here. I used format RAT. Okay. But there are other formats in MATLAB, and you can look them up. If you want like decimals and things like that, there are other formats you can use. But I have mine in format RAT. And then here's the matrix A. then there's the thing there. Okay, so one eigenvector is negative I over 2, 1. The other eigenvector is I over 2, 1. So complex conjugates, of course. Okay, so if one of my eigenvectors is negative 1/2 psi 1, could I have a more convenient eigenvector than negative 1/2 psi, negative 1/2 I 1? Could I have another eigenvector that doesn't have fractions in it? That's right, negative I and 2. So you can always multiply, good. You can always multiply eigenvectors by a scalar to remove the fractions. Okay, so I wanted to just show you that. And now let me go back to the problem at hand. Okay, so hence these are my eigenvectors and eigenvalues that I'll use. Now, remember, our particle is traveling in the real x1, x2 plane. Okay, so if I'm gonna find a position vector, okay, x of t, it has to consist of real entries, no imaginary numbers. And we're going to make use of something we just learned. We learned that x real of t and x im of t are also solutions to the linear system of differential equations. So if I can find out what x real of t is and what x imaginary of t is, this is x imaginary, okay. If I can find out what those are, then I'm going to be in good shape here. And you'll see why. So what I do is I look at one eigenfunction, okay, of my one eigenfunction. And the eigenfunction is, even though, I mean, the eigenfunction, this is my eigenfunction. This is one of them. There are two eigenfunctions, but one of them is e to the negative 2 plus 5 it. That's, you know, that's lambda 1 there, right? That's lambda 1 times the corresponding eigenvector v1. That's an eigenfunction, okay? And the eigenfunction is a complex solution to the linear system of differential equations. But what I'm going to do is I'm going to work with this eigenfunction so that I can get two real solutions to the linear system of differential equations. What I do is I rewrite the exponential part as e to the negative 2t times e to the 5it. I rewrite that part of the eigenfunction that way. And then I'm going to take advantage of something called Euler's formula. Who's heard of Euler's formula? E to the I theta is cosine theta plus I sine theta. Very good, everybody. Very good. So, well, and it can be proven in using Maclaurin polynomials. Just, you know, it can be proven. But the point is, e to the 5it can be written as cosine of 5t plus I times the sine of 5t. Thank you, Devhar. That's right. And now what I'm going to do is I'm going to rewrite my eigenfunction even further. I'm going to take this scalar here, well, with the e to the negative 2t, it's all a scalar, right? So I'm going to take the scalar function here and multiply it by the elements, the entries in the eigenvector. And when I do that, I'm going to get this vector here. Okay, let me know if you have any questions so far. Okay, so we're rewriting our eigenfunction. Okay, excellent, Matthew, thank you. Okay, and then what I'm going to do is I'm going to distribute the I to both of the terms here. And I'm going to distribute the 2 to both of these terms here. Hold on, question. An eigenfunction is when you take an eigenvector and multiply it by e times the lambda t power. That's the definition of an eigenfunction. And eigenfunctions are solutions to linear systems of differential equations. And what we're doing is we're taking this one eigenfunction and we're going to rewrite it. We're going to rewrite it so that I can identify x sub real and x sub I, which are also solutions to my linear system of differential equations. Okay, good question, Matthew. Now, what is I times I, by the way? I times I, that's I squared. I squared equals -1. So what I'm doing is I'm distributing the I for the first component to the first component, and I'm distributing the 2 to the second component, and then I'm rewriting the components as you see here. But I times I squared is -1, so that's where the -1 is. And then, so what I'm doing is I'm compartmentalizing the eigenvectors so that I got like the I parts to the right and the other parts to the left. I mean, why not? We can do that. All right, let's make sure everybody's comfortable. All right, may I move to the next page? Or who needs a little more time to copy? All right, Kevin's good. Okay. Well, now what I'm going to do is I'm going to rewrite this vector. I'm gonna break it up. I'm going to break it up like this. I'm going to rewrite the eigenfunction this way, and by doing so, I've identified what x real is and what xi is. So the eigenfunction is a solution to the linear system of differential equations, but the eigenfunction can be written as you see here. And we showed that then x sub real, that vector, and the vector x sub im are also solutions to the linear system of differential equation. And based off of that, we can write the general real solution to our linear system of differential equations. We get our general real solution, which is, as we've proven, a linear combination. Well, I want to be, it's a linear combination of the x sub real and the x sub I. So this doesn't need to feel, I mean, I know it might seem a little bit, I mean, of course it's new, but this here, we've shown this to be true. We just proved it. We proved this result. And so now I have a general real solution, and I want a general real solution because my x1, x2 plane is a real plane. Okay, it's a real plane, a two-dimensional real plane, and I need to have my trajectory solution x consist of real coordinates. You notice I rewrote x real and x im by, I factored out the e to the negative t. Okay, I mean, that's okay to do that. Are there any questions up to here? Okay, Christy's feeling good. All right, well, of course, now remember the particle started at the point 3,3. So we do have an initial value, and when we have an initial value, we can solve for the constants, the coefficients there, just like you did in calculus 2. So if you do that, then, if you do that, so okay, if we have 3, 3, the vector 3, 3 equals c1 times 0, 2, the vector 0, 2 plus c2 times 1, 0. Okay, so how did I get these vectors? You know, how did I get these vectors? Well, notice the 0 here, right? I mean, how am I getting, like, for instance, how am I getting 0, 2? How am I getting that? Obviously, let me just rephrase it here. I mean, obviously, I'm using this solution here. And x sub 0, what's this 0 a value of? What's that 0 a value of? It's a value of t. And Solomon's right. You're replacing t by 0. So, you know, if you replace all the t's by 0 here, all right, well, you like for the first part here, e to the negative 2 times 0 is e to the negative 0. That equals 1. And then the sine of 5 times 0 is 0. The cosine of 5 times 0 is the cosine of 0, which is 1. So you get 2. And you can similarly see that the second vector is going to be 1, 0. So I didn't write that all out because I think it's easy enough for you to do. But are there any questions? Okay, well, if you solve that, you're going to get C1 equals 1.5 and C2 equals 3. And so we're going to replace the C1 with 1.5, and we're going to replace the C2 with 3. Okay, good, good. People are comfortable. All right, are we ready to move to the next page? All right. Christy's good. Thank you, Christy. Thank you, Matthew. Thank you, Robin. All right, well, let's move to the next page. So again, C1 is 1.5, C2 is 3. And when I put those values in, I can rewrite the matrix like the vector solution like this. Okay, x of t will equal this. So it's just another way to rewrite the solution. And you can go back and look at it, and you'll see that it's easy. It's just manipulating that vector on the previous page. Now what we want to do is we want to sketch a trajectory of the particle. So the trajectory of the particle, okay, so there's the vector x of t here. The vector x of t, remember, that vector consists of two functions, x1 of t and x2 of t. Try to make that nice. Okay, now x1 of t would be equal to e to the negative t times negative 1.5 sine of 5t plus 3 cosine of 5t. x2, that function, would equal e to the negative 2t times 3 times cosine 3t plus 6 sine of 5t. Did I make an error? Oh, okay, there's a time. This should be, thank you, Solomon, there should be a 5 here instead of a 3. Good catch. Man, Solomon, I'm gonna have to get you a virtual candy bar. And Christy for the Discord, I'll have to, well, I could, but I appreciate everybody's help. Everybody's help. Let me put a 5 in there. We're almost done. We might run a 5 minutes over if you can stay an extra 5 minutes. Okay, so now when we think of cosines and sines, you're welcome, we think of what? Cosines and sines. We think of what kind of motion? What kind of motion involves cosines and sines? Circular motion, that's right. And so what's done is there's a trajectory of a particle. right here. And this is a figure 6 actually from your book. Figure 5, I should say. Figure 5. Hold on here. In section 5.7, figure 5 goes with example 3. Now in example 3, they've actually, if you look at that problem, it's, well, we worked with the numbers, but it actually comes from a current voltage problem. If you look at example 3 in the book, but we went right from starting with the matrix A and the initial value. So we're fine. Everything's good. So now the origin here is a spiral point. It's a spiral point, but the origin is an attractor, because look at this e to the negative t. What happens to e to the negative t as t goes to infinity? What is this approach as t goes to infinity? It approaches 0. So that means the solution, as time increases, okay, the solution approaches the origin. And you notice that they draw different trajectories here, and they all approach the origin. Our particle, of course, starts at x sub 0, which is 3, 3. Now, what's drawn here is spiraling motion, and I believe in my math lab for these kind of problems, they have a picture. I've not shown you how to draw this in MATLAB, but don't worry about that. In the homework, they'll have pictures, and you have to find the right picture. I mean, that's how that would work. Or they might just say, talk about it. Talk about the particle. Is it spiraling inward, outward? This is spiraling inward to the origin. But look, it's spiraling inward, and it's going what? Is it spiraling inward counterclockwise or clockwise? Is it spiraling? I mean, clocks are still, I hope you can read time on a regular clock. We are going counterclockwise. Okay, maybe this day and age, maybe you know, I don't know. Digital's very popular, right? But the question is, you know, how do we know that the particle's spiraling counterclockwise into the origin? Well, it's actually not hard to see this. What I've done here is I've written down dx1 dxt when I'm computing the derivative dx1 dxt when x1 is 3 and x2 is 3, right at that initial point. And when and you know, of course, these numbers, the -2 and the -2 and the negative 2.5, they come from our matrix A, right? Those are the, and so at 3, 3, the x1 dt is negative 13.5. For dx2 dt, okay, at 3, 3, dx dt is equal to 24. It equals 24. And again, these values here, these values of 10 and -2 come from the matrix A. And you get 24. So you know the values of the derivatives at that point 3, 3. And this is the key to determining how the particle is moving and why it's moving counterclockwise. Because what I've done here is at x0, I've drawn a delta x2 and a delta x1. How many have seen that kind of thing in calculus 2? Okay, right triangle, delta x1. I mean, you're used to delta x and delta y, but you've seen that, right? So the thing is, delta x2, delta x1, the ratio of these differentials, and I'm looking right here now, the ratio of these differentials can be approximated by dx2, dx1. But we can write dx2 dx1 as dx2 dt over dx1 dt. And we know those values. dx1 dt is negative 13/5, and dx2 dt at 3,3 is 24. So delta x2 represents the rise, right? So you're used to delta y, but in our picture, delta x2 is the rise, and delta x1 is the run. Well, we are going to be rising a positive amount, 24. Okay, and so we go up. From x naught, we go up. From that point, we rise up. And then dx1 is negative 13.5. That means we run to the left because the run is negative. And so after a period of time, okay, the particle has to, you know, this point here would be after some time's transpired, but the particle is moving then, it's committed to moving counterclockwise. And this is the reason why. Or this is one way to see it. How many think that's pretty cool? Yeah. Yeah, I mean, this is like this is great. This is great stuff. Great stuff. And this is what section 5.7 is about. And so now you've had a very good lesson on differential equations, section 5.7. Are there any questions before I stop the recording? Okay.